Okay, we ran into another glitch with the camera, but we were just looking at the sketch of the upper hemisphere and the behavior of the gradient. Now, we said that the gradient starts at negative 2j along the y-axis, where x and z are both 0, and it's going to be negative 2j here, it's going to be negative 2j here. So we see that the flux is coming out of the surface here, going into the surface here. Now, as we move in the positive x direction, the I component starts getting bigger, so that we still have the negative 2j, but the I component gets bigger and bigger until we finally get here, and we have a vector that comes out 4 units in the x direction, comes over 2 units in the y direction. Then as we move through positive y values, our x values start to decrease again, and the negative 2j remains, so that at some point the flux will become tangent to the circle. Up to that point we'll have a net flux out of the circle, but then the flux will start going into the circle. Now what we have on the flip side of this circle is symmetric with what we have on this side. The x's become negative, so that the x components will be negative. You can kind of see how that's going to work. Now, as k gets bigger, we start adding a component away from the xy plane until at x, well, along the z-axis, this thing intersects the z-axis here. X is 0. We still have the negative 2j. We're going to have a 2zk. Remember that z equals 2, so that the vector is going to look something pretty much like this at the very top of the sphere. And as we move up out of the xy plane, these vectors will start getting a significant z component, still maintaining the j component, negative 2. And I'm not going to draw a whole lot more. We're going to have symmetry over on this side, so it's going to come back sort of like this. And I drew those wrong. I was thinking z symmetry, and I drew it as if it had y symmetry. In any case, the vectors will look sort of like this, always with the y component of negative 2, eventually going inward a bit. And you can imagine what the field would look like as we move around the sphere. The point is that from this sketch, we see that we appear to have more flux leaving the sphere than entering the sphere. So let's go ahead and set up an integral to find out if our conclusion from the picture is right, and to find out exactly what the flux would be. Now remember that the flux of this scalar function is just the direction in which the scalar function is increasing most rapidly, and the magnitude of the vector tells us how rapidly it's increasing. Okay, our sphere is x squared plus y squared plus z squared equals 4. We're just doing the hemisphere. We'll take care of that when we set up the inequalities to describe the region. We project this sphere onto the xy plane. We get the circle x squared plus y squared equals 4. And of course that's the circle. In the xy plane. And the sphere would be x squared plus y squared plus z squared equals 4. So we know that we're going to partition the circle in the xy plane and then consider surface area increments lying above the partition regions in the xy plane, so that we're going to get ij increments within the xy plane of area delta x by delta y, sample point is going to be xi star yj star, and the point on the sphere corresponding to a point xi star yj star in the plane is going to be xi star yj star square root of 4 minus xi star squared minus yj star squared. That's simply because the z coordinate, if x squared plus y squared plus z squared equals 4, let's write down the reasoning here, x squared plus y squared plus z squared equals 4, so that z is going to be plus or minus the square root of 4 minus x squared minus y squared. Now we're only talking about a point in the upper half plane because we specified the surface as the upper half of the sphere. So there's only one point on the sphere corresponding to a given xi star yj star, and that point is this one. Okay, now normal to the level surface, our gradient. Let's first state the result that we might have lost track of since the last time we used it, that any normal the normal to any level surface of a function, the normal to a level surface of x squared plus y squared plus z squared is just the gradient of x squared plus y squared plus z squared. The gradient is normal to a curve or to a surface, or gradient is normal to a level curve or level surface of a given function. So the gradient of x squared plus y squared plus z squared is easily calculated. So at any point x, y, z, the normal vector is 2xi plus 2yj plus 2zk. There are other ways to get the normal vector, but since our surface is a level surface of a known function, this is probably the easiest way. Now, why do we want to find a normal to this surface? Well, because our flux is defined to be the dot product of our function with a unit normal multiplied by the area of the surface increment. So here we have a normal vector. How do we get a unit normal? Now let's just do that calculation over here. And it's very straightforward. We simply divide the normal vector, which we just obtained, by the magnitude of that normal vector. And when we do this, you can work out the details. This denominator is just going to be the magnitude of 2x quantity squared plus 2y quantity squared plus the quantity 2 times this square root squared. When you write all those out and add them up, you end up with 16. And the square root of 16 is 2, so that the square root of 16 is 4, so that when you divide through this vector by 4, you get this. And you can verify that this is a unit vector. Again, you can take the square of this, the square of this, the square of this, add them up, expand squares, simplify, and you'll find that the result is 1, that this vector has magnitude 1. This is a unit normal. So at this point, if we go back to our picture, we've got our vector field more or less correctly sketched, and we've got unit normals. Okay, so let's say at this point we've got a unit normal which points straight away from the origin. At this point we've got a unit normal. Here we've got a unit normal. Let's see, that one should be a little longer and pointed away from the origin. At every point we've got a unit normal. Okay, up here we got a unit normal. Up here our unit normal is just in the k direction. Down here it's about like so. At every point here we've got our vector field, our del f field, our gradient field, and we've got a normal vector, and they're generally not parallel. At this point they're maybe pretty close to being parallel, but at other points that won't be the case. What we're integrating is the component of the vector field in the direction of the unit normal, the f dot n. We've got the f function, our gradient, and we've got a normal vector, and we've used that to find the equation for our unit normal vector. Our surface area increment is delta Sij, which is delta A over cosine gamma, gamma being the angle between the normal and the k vector. And this goes back to what we did with basic surface area integrals. And what we have here is exactly the same as what we had there. The normal vector is evaluated, of course, at our sample point xi star, yj star, and actually that should be xi star, yj star, f of xi star, yj star, because our normal vector does have a z component, but we've taken care of that by substituting the 2 square root of 4 minus x squared minus y squared for the z. So if we evaluate this expression at xi star, yj star, we have the expression for the unit normal at that point. Okay. The component of the field perpendicular to delta S is then just del f dot n, as we were just discussing. And that's going to equal what? Doesn't look like I've got the whole thing here. Okay, I've got the del f. I didn't write down the n, and I don't have room to write down the n here, except to just write it as n. But in the next step, I've pretty much written it out. So our del f is this. Our n is just what it is up here, except our x, it becomes an xi star, our y becomes a yj star, and this square root here might be written a little bit small, but I've written it out a little bigger here with an arrow to indicate that's what we have down here. In other words, just substituting xi, yj into the expressions for del f and n, we take the dot product, and you can verify this is what we get. Two xi star I left the I vector off of that. 2xi star I will be dotted with the xi star over 2I to give us xi star squared. The negative 2j with the yj star over 2 to give us the negative j star, yj star. And the 2 times the square root with the same square root divided by 2 just gives us the expression inside the square root, and we combine terms and we get this expression. So the flux is the area multiplied by the perpendicular component of the field, and that's this expression. It's del f dot n times delta x delta y over n dot k. Delta Sij, remember, is just delta x delta y over n dot k, the delta A divided by the cosine of gamma, if you recall. The del f dot n is just this, and this is the expression we get, this numerator being just this dot product, and this denominator in this multiplication by 2, I just filled this in, n dot k for our point xi star yj star is just the expression for the normal vector, which is written pretty small here. You might not be able to read it, but it's just